Okay, so the first thing I want to talk about or mention is just the learning targets for this section. So we're basically looking at electrons. We focused on neutrons and protons earlier with talking about isotopes, and now we're going to kind of look at how electrons kind of move in the atom. So we're kind of mentioning a little bit about the electromagnetic spectrum and just specifically the visible light section. We're also going to talk about the or distinguish between absorption and emission, and we're going to talk about how light can be produced by absorbing and emitting energy from an electron. So I have a short little video here.
We've got six metal salts here. We have calcium chloride, copper chloride. You'll notice the copper is green, the rest of them are colorless. And then we have some lithium chloride, potassium chloride, and then we have some sodium chloride. That's good old table salt. And finally, strontium chloride. I'd like to note that historically, this experiment has also been done with barium chloride, but it's very toxic and should be avoided. Now we've put the ends of the splints in the six solutions and we let them soak overnight. And we're going to put the tip of the splints in the flame one by one, and we'll see the characteristic color that the metal produces. Remember, when you're lighting your burner, to use a striker. I've got one here. If you don't have strikers, you can use a match. But remember to light the match before you turn on the gas. Make sure the air vent on your burner is closed. Turn on the gas, light the burner, and then adjust the airflow. So now we're ready to begin. As you see, I have the Bunsen burner lit, but you actually can't really see the flame that well. It's almost a colorless flame. So the first solution I'm going to do is calcium chloride. You can see I kind of keep it moving in the flame because I don't want my splint to catch on fire. But you can see that calcium has a very deep orange color.
So as she goes through, pay attention to the different
Second one I'm going to
colors
do is
that
the
you
copper
see.
chloride. You can see it's got a deep green color. And not surprisingly, its flame is a beautiful blue-green. I think this one is one of my favorites. The next one is lithium chloride, which has a really deep red color. Next is potassium chloride, which is a little hard to see. You can see it's got like a pinkish violet color. I think it's the hardest one to see of all of these. Next is our sodium chloride. And it's got a nice, beautiful yellowish orange flame. And finally, we have strontium chloride, which is again red, but this one is a little more orange red.
So what you should have noticed is that different elements give off different colors when they're put under the flame. So what that basically means is that those elements, when they're heated up, they're absorbing energy, and when they're releasing that energy, they're releasing it as different colors of light. So we're going to kind of talk about how we get those different colors. So you should pause here if you don't mind, and go ahead and work through the first section of the POGLE. I do have the colors already done for you for section one, for model one. So if you don't have colored pencils, that's okay. That's not necessary. It just kind of gives you a good visual. But go ahead and answer, pause here, go ahead and answer the questions for model one. Okay, so you should have paused and answered the questions. And so here, I just want to kind of go over just kind of this kind of key point right here. So you're looking at the relationship between the wavelength and the amount of energy. And so what you should have noticed by looking at your chart is you should have seen that the longer the wavelength, the lower, I'm just going to put an arrow, the energy. Let me, I don't know if I can change how thick it is. That's okay. So the lower, okay, the lower the energy. So it's an arrow going down. There's a small amount of energy. The shorter the wavelength, the larger amount of energy you have. So what we're looking at when we are, let me erase this, sorry. When we're talking about energy and waves, are we're here you have the electromagnetic spectrum, and this is basically just a list of different types of energies and where they would fall based on their wave characteristics. So, on this side of the spectrum, you have the long wavelengths, and on this side, you have the short wavelengths. So, based on the changing in my wavelength, I can also talk about the changing in my um, amounts of energy. So over here with my long wavelengths, okay, I actually have a small low energy. So you can see that energy increases as we move towards the shorter wavelengths. And so when we're looking at talking about electrons, we're really just looking at this section of visible light. So we can see how much energy is actually being released based on what color it is, which is what you saw in the chart. You were looking at um, the different colors corresponded to the amount of energy. So you can see red is very low energy, longer wavelengths, and then blue, violet is the higher energy section. So here, just to kind of review, so you can kind of get a visual of what I'm talking about when we're talking about how electrons are moving in the atom. We have the structure of the atom in our Bohr model here. And if we look over on the left side, um, you can see how we have our protons and our neutrons in the nucleus, and then we have our electrons that are kind of circling around the outside. So if you look at the size, it's kind of drawn here for you, but the protons are much larger than the electrons. So they have this very strong positive force. Electrons have this negative force, and so they're actually, or a negative charge, and so they're very attracted to each other. If you think like a magnet, right? You have a positive end and a negative end of a magnet, and they're attracted to each other. So this the pull that these protons have on the electrons is kind of what's keeping the electrons in their appropriate energy level. Okay, that's keeping the shape of the atom as a circle. It's just how gravity works on the Earth. The center of the Earth is pull of gravity is very strong, so that's what pulls in the outside of the Earth into a circle. Everything's kind of pulling towards the center. So when we're talking about in this next section, you're kind of going to start looking at how energy is released and absorbed, and it's important to kind of um, know some keywords. So if you see anything like excited electrons, okay, what that's meaning is that you can see how here this electron starts down in our first energy level, and you have some energy being absorbed, and that what's going to happen to that electron is it's actually going to be able to jump to an outer energy level. So you may ask, well, why can't it jump by itself? Why does it need energy? Well, that goes back to this attraction between these positive and negative charges. If I have two particles that are pulling towards each other, if I want to pull them apart, I'm going to have to apply some energy to that. So if I want this electron to move from close to the proton to further away, I'm going to have to actually give some energy in and pull some of that energy, or use that energy to pull that electron away from the protons. Okay, down in the bottom here, you can see where I now have energy being released. Okay, so it's the electron is actually returning back to the ground state. Okay, and let me wonder if I can drag this. There we go. The electron's moving back to its ground state here. That's the original state, the original energy level that it was on. So it's moving back, and as it does that, okay, it's attracted to that proton. So it's really easy for it to move back down because it's just being pulled by the proton. And so when that happens, it actually releases this energy that it had just absorbed up in here. So this is just kind of showing you a picture of how different amounts of energy can be released. So if you notice this blue arrow, okay, obviously that electron started somewhere down on the first energy level. Okay, it absorbed some energy and jumped up, and now as it falls back down, it's releasing that energy back out. Okay, and if you notice the difference between the blue and the red, I can actually compare my wavelengths. So from here to here and here to here, my red arrow actually has a lot longer wavelength, which means it has lower energy that's being released. Okay, and that makes sense because here, this arrow only jumped up and fell back down one energy level, whereas this arrow, the blue arrow, jumped up and fell back down 4 energy levels. Okay, so the more energy levels that it's able to jump, that means it had to absorb more energy and able to get that far away from the proton. And then as it falls back down, it's going to release that same amount of energy. So we should be able to circle some of these words here. I think it says okay if you want to skip module 2. I believe it is. So this information right here is for module 3. So if you'll pause, then you can kind of come back and we can go over some of this information here. I believe it might be at the end of 2 actually. But you can kind of skip the beginning of 2, where it has this talks about the spectral lines. So just pause here and answer these questions. Okay, so here, this is just reviewing what we just talked about. So electrons and protons, okay, they attract each other. And as an electron gets closer to the nucleus, so that electron and proton are getting closer together, that attraction is actually going to get stronger. Okay, because the closer that it gets, the stronger it pulls. Think about a magnet. If I'm trying to, get 2 magnets to stick together, I have to get them in, close enough for them to kind of get that final pull. So for an electron to move from an energy close to the nucleus to far away, right, it's going to have to gain some energy so that it can overcome that attraction. And when that electron wants to move back down, so when it moves back down almost immediately, it's going to lose energy. So this part we can kind of do together if you want to. If you'd like to pause it and give it a try, that's fine. I do have it labeled on yours, so it does make it a little bit easier because I've already labeled it, whereas the slide is not labeled. So if you're looking, if you notice, I did write how this first section of Model 3, I think it's question 19, you were looking at this B, this atom B. Okay, so it's asking you questions. So you can pause it here if you'd like to go ahead and try yourself, and then you can come back and check your answers. So this electron transition, okay, it's moving from an energy level 5 to 2, so it's moving back down. So closer to that positive proton. So it's just moving closer where it's attracted, and you can see this little wavelength here that's exiting. So that means that this electron is actually releasing energy. Okay, and it's moving from a higher to a lower. We can see that, right? And then is light absorbed or released? So I know that when that electron moved up, it had to absorb energy in order to separate from those protons. So I know when it moves back down, this right here is actually that energy that's just being released. And remember, we can see certain wavelengths of energy as light, as a color. So that means light is being released. So for the next ones, we're basically I've already labeled them. So question 20, it's talking about labeling them, and then it's talking about can we figure out what color they are based on how much energy they release. So the first thing is probably easiest just to figure out which one is releasing the most energy and which one is releasing the least amount of energy. So if I remember or go back, remember the longer the wavelength, or if I can do text, like a text box. Maybe right here. Nope. All right, I tried. So the longer the wavelength, so maybe I'll just do higher the wavelength, right? The lower the energy. So if I look at my atom A, okay, it has a very short wavelength, whereas the atom D has a very long wavelength. So I know that this atom A is going to have very high energy because the wavelength is very short, whereas this atom D has low energy. And that makes sense because if I look at the distance that my electron traveled, right, the very small distance really only required a little bit of energy, whereas over here I moved up 4 energy levels, so that required quite a bit of energy. So now I can think about the colors. Well, I know that the highest energy, that's my violets, put a V, and then I know my low energy, that's my reds. Okay, and then you could fill in those with the middle colors. And that is it. There's a video in the slides. I'm not going to show it. But you can Google it if you're interested in it. But I don't want to put too much more time. But this is how neon signs work. There's some element. There's a gas in there of a certain element, and once it's charged with that electricity, it's given energy by electricity. Those electrons start moving to an excited state and back down, up and down, up and down, and it releases that energy in the form of light. And so that's how we get that bright glow, is just that energy being released from the electrons. So that's it for this section. Hopefully that helped you fill out some stuff if you had questions. If you still have questions, then please message me.